Hello and welcome to Creating Chaos and Hard Defaults. I look forward to presenting some ideas about debugging to you. Happily, to talk about debugging, we need to start with some really good bugs. Hard defaults are one of the boogeymen of the embedded software world. So many of our traditional campfire stories start with, "And then my processor mysteriously rebooted." And then the story goes on to describe weeks of painstaking work, only to find a typo deep in the algorithm stack, in code nobody has touched in months. Wait, let me introduce myself. I am Elecia White. If you like this talk, I have a book and a podcast. The book just came out in the second edition, and there is about 40% more material, including the chapter this talk is based upon, chapter 9. So let's get started creating some chaos. Here's some code that takes a name from user input, but never checks to see if the name exceeds the amount of memory allocated. Presented here, this example, it tells what is wrong with it. However, historically, bugs of this type have been exceedingly prevalent and dangerous. Because of the way the code works, you can use it to take control of the processor by putting in a name that is intentionally longer than max name length and overriding part of the stack, which lets you jump to whatever code you want, including the code you might have just entered through the name variable. Okay, but how does that work? This is a talk from EOC 2021, and I gave it about how to read memory maps. Sadly, today's talk does not have such a pretty graphic. And while there are stacks in Ramlandia, that isn't what we're going to need to see when we talk about smashing a stack. Instead, I want to show you a different sort of memory map, focusing on Ramlandia, RAM. The start of the memory is at the top of the diagram, and the highest address is at the bottom of the diagram. There's this whole heap grows up, and stack grows down, with arrows pointing the wrong way. I've tried to set up this diagram in many different ways, and there's always some form of confusion, so I decided this was the one I wanted. Trust me, I tried very hard. Anyway, here it means that the stack grows down because it uses decreasing addresses as new functions are called. What I'm interested in here is actually towards the bottom, the stack pointer. Let me zoom in a bit on that. The stack, note the definite article, refers to the system call stack that lies behind every running program in a designated section of RAM. For each function called, the compiler creates a stack frame that contains the function's local variables, parameters, and the address to return to when the function is finished. So there's a stack frame for every function call, starting with the reset vector, and then the call to main, and then whatever you call after that. If you have multiple threads or an operating system with processes, threads, tasks, those usually have individual stacks for each one. But I'm just going to focus on this one. And with this in mind, with the stack frames and what's in them, I want to go back and look at that code again. The one with the unbounded input. We have an array created in a function. So it's a function variable, which means it's on the stack. That's the name array with max name length. Now we pass this name array into another function, unbounded fill from input, which then goes outside the space allocated for name array. What do you expect to happen? The trash the stack function is the calling function in this diagram. Its variables, including the name array, are on the stack. When the unbounded fill from input puts too many things in the name array, the stack frame gets overwritten. But which stack frame? It is the one used to call trash the stack. Unbounded fill from input stack frame is fine. It returns without a care in the world. Even the trash the stack function may be able to return. Depends on how far out of bounds we go, whether or not we actually overwrite that return address to main function. If we go far enough, the name array will overwrite that and we won't be able to return. Think about that. We will successfully leave unbounded fill from input, but we won't be able to return from trash the stack. When we try, we'll go somewhere else, depending on the input from name array. That's why these types of bugs are so interesting. When they happen and where they happen has nothing to do with where the problem is. And the symptoms depend on a lot of different factors. Let's take off the agent of chaos hat for a little while and think about how to debug this behavior without knowing what would cause it. You have reports of a bug. It's unexplained and odd behavior. No one gets the same set of symptoms. What do you do? If you haven't seen this, well, you should, because it's funny and because it is so very, very true about how we tend to debug things. However, this is more along the lines of the best advice I have. For the path on the left, it seems obvious that the first step is reproducing the bug. And this is a critical step. It doesn't matter if you have to hop around on one foot and cluck like a chicken. You have to make the bug happen again and again. Steps that shouldn't matter still end up needing to be documented, because if that's how the bug gets reproduced, that may be a symptom. And once you have created a minimal code set that can still reproduce the bug, well, then you can post it to a vendor forum or get some help or walk through the code. More likely, before you've gotten a truly reproducible bug, you've gotten stuck. And that's where you need to go to the other path of explaining the bug. You need to switch the strategies. I have found when someone asks me for help with a bug, the first thing I need them to do is to explain what they were trying to do. And I am no longer surprised when they walk away halfway through their monologue. Explaining the bug helps you understand it better and helps you see the disconnect between what you intend to do and what is actually happening. It's more of a thinky type of action than the typey type of action that goes into reproducing the bug. And I don't mean to say that describing the bug is easy. Saying it doesn't work isn't enough. What doesn't work? How is it different from expected? Is it a single version of code? Is it a single board? You need to be really detailed. And explaining the bug does ask you to assume that the bug exists, which is often harder than it sounds. Though explaining the bug only gets you so far. You can develop lots of theories and ideas, but then you need to take some data, which means going back to reproducing the bug. You can't fix what you can't measure. So let's move on to hard faults. And realistically, I'm not going to do the topic justice. In the end, I will tell you to go read Chris Coleman's blog, the memfault interrupt blog post on debugging hard faults. Or I'll tell you to avoid creating hard faults entirely, which is superb advice, but totally useless. Anyway, let me take a step back. What are hard faults? Hard faults are interrupts caused by the processor identifying a potentially catastrophic issue related to the execution of the code. These are usually non-maskable interrupts, NMIs, so you can't disable them through the interrupt system. However, I like to think of hard faults as the processor sending you love letters. How do you create hard faults? Did you really think I was going to tell you how to avoid them? No, the best way to understand these exceptions, these faults, these horrible interrupts is to see what they look like when you aren't frantically trying to fix your code. As painful as hard faults are to debug, Be glad they exist. At least something is trying to tell you what went wrong. I'm going to show you some hard faults, how they happen, and what the processor can tell you. This list here is not all inclusive. Some may not even be faults on your system. Hard faults are very processor dependent, so they give you the opportunity to learn a lot more about the core of your processor, whether you want to or not. Now, I wrote some terrible code for you, and I really hope you appreciate it. You can find the Git code on GitHub, so you can try it yourself. If you run the terrible example code, you can learn how your system responds when your code does terrible things. I'm going to be using a Nucleo L46Z board with the STM32Cube IDE. I'm afraid that if I use VS Code, I will tend to use key commands and wander through too quickly. STM32Cube is free and very easy setup if you are using an ST evaluation board like I am. And I chose this Cortex-M4F board mostly because it was sitting on my desk when I started this talk. And I'm not going to be talking about things that are super processor specific. Oh, I know, I just a moment ago said that hard faults are very processor specific. And they are, but how we debug them and how we look at them really isn't. I loaded this code and it has stopped in main. I have a breakpoint at do some hard faults. So let me run to that function. And it will hit my breakpoint. Let's see what's inside this code. Obviously, dividing by 0 is wrong. If anyone successfully does that, I have it on good authority. The action will create a singularity, causes a black hole that devours the galaxy, possibly the universe. How would I know? But what happens if you were to call this code onto a Linux computer? You'd get an abnormally terminated process, a SIG-SEGV or a SIG-FPE or a SIG something. If I run this, however, I end up in an infinite loop. I can see how I got here by looking up here at the stack trace. This is the IDE untangling the stack frames for me. So I can see which functions called which. There's some strangeness because of the hard fault, but we can get back to divide by 0 and see what actually went wrong. We can find out more by looking at the processor registers. This is the CFSR, Configurable Fault Status Register, and it says divide by 0. But how would you even know to look here? Well, you need to look at the vendor user guide for your processor. I have a Cortex-M4 here. I'm looking at the Cortex-M3 devices generic user guide only because it is prettier and they are functionally the same for this register and the others I'll be looking at today. So the CFSR tells us about different kinds of faults we can get on this processor and which ones they're marked and how they are all set up. Now I can search for divide by 0, but I know it's down here in usage fault status register. It essentially says I have executed a divide by 0 and it all went horribly wrong. So the ARM documentation is where we start to learn about these registers. But honestly, I don't have to get this this hard fault at all. I know I said I can't turn them off with the interrupts, so I can't disable interrupts and not get this. I would still get this interrupt. However, if I reset, I can tell the processor that I'm not interested in this type of interrupt by modifying the config and control register, CCR. And this is, again, something you would need to look at in your processor documentation. And we can see here that this will allow me to turn on or off a number of different hard faults, including my divide by zero. So let me do that. If I set the CCR so div by zero is zero unset, then I'm saying I don't want this to create a fault. And then I can walk through this code. And I get an answer of zero without exploding the galaxy or anything. Let me reset this one more time and run div by zero again. So to my breakpoint, and this time I'm just going to step over it. I'm just going to let it run and get to my infinite loop. So this is an assembly file, but it's pretty straightforward to set up. This is the vector table, and we can see the hard fault handler is here. If we go down in this file, or we were to search through it, we can find that the hard fault handler is set to the default handler, and it's weakly set, which means that as long as we call another function hard fault handler, we can replace this. And until you dig into the code a little bit, your hard fault handlers and unhandled interrupts are likely to go to these default handlers that do resets or infinite loops. Now, moving back to my divide by zero code, it's easy to see what this does. It isn't so easy when it's buried in thousands of lines of complex signal processing code. Note that the goal of the processor fault handlers, which look just like interrupt handlers in that they are in the interrupt vector table and are generally handled like interrupts, but the goal of these hard fault handlers is to narrow down where the processor was when the issue happened. The stack can be used to figure all that out, including where the processor was when the fault occurred. And we'll look more at that in a few minutes. Moving on though, I'm going to comment out divide by zero and look at writing to null. Now, I don't know about you, but I certainly have written to null in the past. But we all know you can't access a null pointer. But why? A null pointer is a pointer that's set to zero. So the zero might be in memory. It could be the beginning of your flash or the beginning of your RAM, but more likely it's just an address in memory that doesn't exist. It doesn't point to any associated memory. And we traditionally set pointers to null so that we know the pointer isn't supposed to be used. Now, as you look at this terrible code, note that the global pointer uninitialized is uninitialized, but as a global pointer, it's sneaky. Global variables are automatically, implicitly set to zero. Same as those that are more explicitly set to null. Writing to zero when it is flash or has no actual memory associated with it feels like it should lead to a hard fault, probably to data access or bus fault. But wait, I just stepped through and didn't get any failures. Why do things never fail when you want them to? In this case, my processor has a memory protection unit that I need to set up before getting these types of hard faults. Do you start to see what I mean by hard faults being gifts? Code like this shouldn't run. And it isn't only null that's the problem. Writing to any address that has no actual memory associated with it should cause a fault if the processor is configured to identify them. The last one in this code, pointer uninitialized. Well, this is set to zero right now, but that's luck. It is a variable on the stack, And if the stack was something else right now, if some other function was called before this, or there was a long call chain, this pointer uninitialized, it's so much worse than a hard fault, because unless you get lucky or the address doesn't matter or it isn't valid, writing to this pointer will work sometimes. Where this pointer is depends on what is currently, or what was previously on the stack, which is a lot like saying it depends on randomness. And so this function doesn't cause a hard fault, but I sure wish it did. Now, instead of having you watch me set up my MPU, I want to show you the next routine. This is one you really should only run for fun, never unintentionally. Because in this one we have bad code. This is not the normal level of bad code, but instead code your processor cannot run, just as you cannot touch your nose to your elbow. The illegal instruction execution function executes E0000 as an instruction. This isn't a valid instruction on my processor, so I always get a hard fault. Following the CFSR, the configurable fault status register, I can see I have an inv state. That means the processor has attempted to execute an illegal instruction. And we can find that back on our web page. But it doesn't hold any more information than you really shouldn't have executed that instruction. It's not, it's useful, but it's not useful. And the cause is obvious in my code, what's happening. But the easiest way to do this unintentionally is to have a function pointer go awry, or having smashed a stack by accident, or sometimes you want to run from RAM because it's faster, or because you're modifying the flash. And then when you run from RAM, there's the problem that if you go outside of your bounds, you could overwrite the code, leading to illegal instructions and other forms of chaos. So we've seen some hard faults, but there's more to it. And instead of looking at even more of them, I want to look a little bit on the handlers and replace that infinite loop with something a little bit more useful. So let's set this to go and compile and load. And then I'm just going to let it run again, running that illegal instruction so that I can get to the hard fault. And this is some assembly code that runs and does some interesting stuff with the stack, so that when we get to here, our actual fault handler, we have all of these things in an easy to parse package. So I'm going to go down to my software breakpoint, and now all of my variables are filled, including a bunch of my stack related variables and that important fault status register, hard fault status register, debug fault status register. This starts to show you which of these registers you want to keep track of. So now if we look at the program counter, the PC, and we look at this illegal instruction execution, this is the same. This is 8,055,0, and this is +1, which is common. I'm not going to talk about that. But our PC tells us where the problem occurred, which is a big hint for where we should start looking at our debugging, or at least starting to add things that will tell us what went wrong. And we don't need the IDE to do this for us. We can look in the disassembly ourselves and see what's at this address. I put the program counter into the disassembly window and can see where the code was run. These other registers can tell us what failed. For example, R0, 2004 FFE0. Well, now if we go back to here, that's where instruction was. This seems like a big clue. And this is why I needed to tell you about smashing the stack. See, all of these things, all of these different variables that are available to me because of this hard fault handler are not secrets. It looks like there may be something. I don't want you to think that there's something between your IDE and your debugger that's secret and special. There's no extra information to tell you where the backtrace is. The IDE is just parsing the stack frame so you don't have to. But that doesn't mean you can't. You can do that and add a bunch more information. Let me show you one more handler. This one is from memfault in that blog post that I keep mentioning, but that I will have a link to. And let me reload this. Memfault has some delightful code that collects all of these useful registers into a structure, which they call the context state frame. And I'm going to just keep pushing go until I get to my hard fault handler. And again, I have a software breakpoint at the end. So they have used their assembly code to put everything into context state frame. And then I have my code, which is going to take this core dump and fill it up with stuff that I found interesting. Now, could I fill it up with everything that we had before? Absolutely. And sometimes there are things we want to do that for. But I'm taking my core dump and I'm putting it into a special section of RAM, a special attribute section of RAM, which means that I can go into my Flash linker file and I can see where I want it to go in RAM, and then I can put it into a special section in RAM in my linker file. And when my processor boots up, it won't zero it out. I've set aside this RAM and I can use it to send myself core dumps. Upon boot, the processor will look for this core dump key. And if it's there, it will send the data to the server if we have interrupt, or store it in a log if we have flash, or print it on a serial line. However it happens, this love letter won't get lost. And I can use it to debug this core or this hard fault, even if this device is far away from me. Now, there is more to that file, along with more tips on you can use for debugging hard faults. In the meantime, let's see what else I've got on my slides. Right, we did this already. Still, I have these slides. Let's see what I forgot to talk about. I talked earlier about reproducing and explaining what the bugs could be. This is a list of possible things a bug could be, possibly cause a problem. I mean, look one up for your processor, of course, but... Oh, and I promised to tell you how not to create hard faults. The best way to avoid hard faults is to not create them, and the best way not to create them is to avoid writing code altogether. Actually, you know, even better, avoid technology forever. Well, that seems unlikely. Let's see if we can do a step better. If hard faults are love letters to from the processor asking for help, compiler warnings are like mundane traffic signs. It's easy to miss a no turn here sign or knowingly go through a yellow light. Most of the time, the consequences for ignoring warnings are nothing. No big deal. However, some of my hard faults today could have been found by enabling the compiler warnings and fixing them. Spending time to remove seemingly trivial compiler warnings is necessary so you can get to the incredibly important ones. Pointer uninitialized is used uninitialized in this function. Seems bad. Function returns address of local variable. Sounds like a good way to blow the stack. These are important. And you fix the ones that are like cast necessary so that you can see these important ones. So once you've reproduced the bug and explained the bug and tried everything you can think of, maybe go back to cleaning up those warnings you've let accumulate. Or even better, don't let them build up in the first place. And when hard faults do happen, I hope I've given you a few tools to identify, document, and debug them. However, since you'll probably need something to go on, I strongly recommend the Chris Coleman's blog post. Hard faults tend to be tricky to debug. They're often the Heisenberg bugs, the ones that happen occasionally, but never when you're looking. So before I go, I want to spend a few minutes on the general theory of debugging impossible bugs. We saw this earlier. Let me make it a little bit more explicit. The impossible bugs are the ones we usually can't reproduce. Once we can reproduce them, we can corner and catch them. So the first goal is always to find a way to reproduce the issue, ideally on demand. Except sometimes to figure out the bug is even happening, we need to add some instrumentation. So that when the bug happens, you have a memory dump, or at least a log message telling you it occurred. Sudden reboots won't always come with customer complaints. Sometimes they just ignore them. And you need to measure what is wrong in order to figure out how to reproduce it. Some of your basic instrumentation might include simple logging, a RAM history of the last 100 tasks or functions, core dumps, reset causes that are checked and flagged at boot, logic analyzers, and oscilloscope traces that are triggered by a GPIO line in your fault function. And then your forensics process is all about gathering all the data, preferably on multiple instances and multiple boards. And then we go looking for clues, some value that's no longer in range or values out of sync. And then we try to correlate between clues and symptoms. But to do all that, you have to start with reproducing the bug. So even though it takes 10 seconds of chanting, and followed by turning the board on its side after it boots, and that all seems like unnecessary voodoo, you can't take the steps out until you can reliably reproduce the bug. When I asked several senior folks about their debugging methodologies, one of my favorite answers was from Bailey. I write down each thing I believe to be true about the system and how it is supposed to work, and how I can prove that each one of those is true. She goes on to say that she usually gets hints when she can't think of how to prove the things are true. I like this because it's about comparing what you think is happening and measuring what is actually happening and finding the discrepancies. Now, in my list here, in step 2, I suggest using inductive reasoning to find the cause. It's backwards from most debugging. Instead of finding the cause for the problem, you find all the possible causes for the problem, for the symptom. You can even go further. If you wanted to make this happen, how would you do it? And there's a tendency to assume some very complex things, some crazy edge case. But so many of these bugs, these really hard bugs, turn out to be a little bit of pointer juggling that went wrong, a typo, or a loose power cable. Still, if you've exhausted all of the dumb little things, venture into bigger worlds, unknown things that might be happening. Memory is always a big one, but there are plenty of other causes. And given we're embedded engineers, we get to have both hardware and software causes, which is double the fun. And this is definitely not a complete or detailed list. Your list will depend on your symptoms, your processor, your system. Finally, you aren't a robot. When you reach the end of your concentration and enter the pit of despair that things will never work and it is all your fault, or you generally run out of things to try next, take a break, go for a walk, get a snack, talk to someone about something else, get some sleep. Your subconscious needs time and space to process without you constantly handing it more information about the problem. I've thrown a lot at you in a pretty short amount of time. I started with the stack. If you want to know more about fun things you probably shouldn't do, the one with the dollar sign is pretty amusing. If you want to know more about your stack and your registers on your processor, check out the generic user guide for the core of your processor. You can see some of my favorite hard fault posts here. And I really want to highlight the one with the heart as something you should bookmark for when you forget this talk. This is me in icon form. If you want to contact me, hit the link on Embedded FM. If you like this talk, you might enjoy the Embedded podcast or my book, Making Embedded Systems, or the talk I gave about memory maps for EOC 21. Thank you so much for watching.